Okay, so after writing the three-dimensional equation in this form with different components summed up in the energy density, the first model universe for which you are going to try to solve this equation is an empty universe. So just you throw away the energy density term and you end up with just the curvature term, right? This A dot square equals minus kappa C square by R naught square. Now this equation has a trivial solution. If kappa is equal to 0 for a flat universe, you also get A dot equal to 0, so it's a static universe. So what you have is that your Robertson-Walker metric turns into a Minkowski metric. This is a flat static universe and special relativity works. Yeah, there is nothing very interesting about this universe. Now, you can also have other values for kappa. If you have plus 1, however, the right-hand side is going to be negative and the left-hand side is a square, so that's going to lead to imaginary numbers, which is not allowed. So kappa can also be plus 1, but not minus 1. Right? And if kappa is equal to plus 1, then you get this, kappa can be minus 1, but not plus 1. So if kappa is equal to minus 1, then you get these two solutions. A dot is equal to plus or minus C by R naught, and the positive solution corresponds to an expanding universe. The negative solution corresponds to a contracting universe. This differential equation, when you write this as dA by dt, has a trivial solution, and you put the boundary conditions saying that T0 T has the value T0 at the present time, you get this simple linear solution. And this T0, coming from this constant, has the value R0 by C. So the age of the universe is just the radius of curvature of the universe divided by speed of light. Right? Which kind of makes sense. These are the only two things that will give you something with dimensions of time. Right? So in this universe, this T0 is also going to be the Hubble time, right? Just by definition of Hubble constant. So Hubble time is just 1 over the Hubble constant, and the Hubble constant is the present value of A dot by A. So just from that definition, you'll find that the age of the universe here is going to be just Hubble time. Now this linear relationship is plotted here as a linear relationship. So the y-axis is just the scale parameter. It's a dimensionless parameter. The x-axis is time. But this has been turned into dimensionless form first by subtracting off the age of the universe, the present value of the time coordinate in the Robertson-Walker metric. Let's say this T0 has that physical interpretation. So you subtract this off from T, and then you multiply it by Hubble constant. So Hubble constant has dimensions of 1 over time. So this product is actually dimensionless. Right? So this is a common way of writing time in cosmological context. So you exactly know what T equals 0 or this coordinate being 0 corresponds to, and so on and so forth. Okay, so now this kind of universe that's completely empty, even though it's simple, it might look completely useless because by definition there are no observers and also there is nothing to observe. But it's not useless because we can use this as an approximation to a universe where the energy density is much smaller than the critical value of the energy density. Right? So in fact, if we didn't have cosmological constant in our universe, if we didn't have a dark energy component more generally, then as the universe expands, this is the kind of universe we would reach asymptotically. Right? So in this universe, by using the solution for the scale parameter, this linear relationship over here, we can actually write the redshift. Right? So this is what we do in cosmology. You observe a distant light source, a galaxy probably, and then one of the fundamental things you can get from that is the redshift. So we can connect this redshift to the time of emission and the age of the universe. Right? So this 1 over z is actually the scale parameter at T0, which by definition is equal to 1, divided by the scale parameter at time of emission, and because of the linear relationship of between A and T in this universe, you just get T0 by TE. Right? And you can write this T0 in terms of the Hubble time, and so the time of emission is the Hubble time, or 1 over the Hubble constant, divided by 1 plus C. So this Hubble constant is usually another observable that you have access to. So by making some observations, you can tell what the time of emission for a photon that's reaching your telescope is. Right? So this is when the light was emitted. The other question that you can ask is from how far was this light emitted, and for that, of course, you go to the proper distance. Right? So this is the standard calculation for proper distance. You write it this way, and so you can turn it into this with the scale parameter, but this is just the co-moving coordinate of the source. Right, so this is the basic result. But what you can do is that when you write it not in terms of the r coordinate but in terms of the time coordinate, you get this dependency on the scale parameter. And because we solved actually Friedman equation for our model universe, we can write an expression for this scale parameter. Right, so you take this. So this is the proper distance, and for a of t, we write our linear relationship that we found. So you just substitute in here in this equation 5.34, and you get the two values, right, at the end of the integral t0 and te. So this is how much so t0 is the time of observation, te is the time of emission, and this is just 1 over t. So its integral is logarithm, and the difference of logarithms is the logarithm of the ratio. So you get this simple result. Right? And again, what you want to do is that you want to actually express this in terms of the observables, the redshift, Hubble constant, and things like that. And you can. So you can just take this t0 by te by using equation 529. This just turns into 1 plus c. And this t0 is just 1 over the Hubble time. So this is c by h0 times logarithm of 1 plus c. Right? And they plot this relationship on the left over here. Again, the dashed line corresponds to the universe in question. Now there is something that looks a bit paradoxical here, that you have these objects that are farther than the Hubble distance, but their signal apparently reaches us over Hubble time, right? So if you look at the redshift, now there is no paradox here, there is no contradiction here. What happens in this case is that this is an expanding universe, that at the time of emission these objects were closer, but at the time of our observation they actually moved farther. So and what we are calculating here, the proper distance at time of observation, corresponds to their current distance, right? Not the distance at the time of their emission. So there's no paradox. The light signal coming from them is not actually traveling faster than light, right? As it shouldn't. Now, of course, however, this brings up the question of, if this is the current distance, what was their distance at the time of emission? Right? And you can answer this question by looking at how the proper distance changes. How the proper distance changes, like the scale parameter, and the scale parameter changes as 1 over c. Right? Again, if you go back to this expression of 529, this 1 plus c is actually a at t naught, which is by definition 1, divided by a at te. The scale parameter at time of observation divided by the scale parameter at time of emission. Right? So the scale parameter changes from time of observation to time of emission by 1 plus c. So the proper distance is also going to change by the same factor. So you divide this proper distance by 1 plus c, and you get your expression for the proper distance at time of emission. And this expression is plotted on the right hand side in this figure here. So it's this dashed line. And one important or interesting feature of this graph is that it has a maximum. Something, of course, could have a proper distance at time of emission larger than what is given here in this universe, and those objects you are not going to be able to observe. Right? So this just goes through some maximum, and there is a maximum for the proper distance at the time of emission. So no object that you observe is going to have a proper distance larger than this at the time of emission. Right? Or like those signals are not going to reach you. Anything which was farther than this at time of emission, after that point it's not going to just reach you, that no signal is going to arrive. So this kind of limits your universe. So this doesn't mean that you're actually limiting the part of the universe, because by going back to very high z, you can actually observe things that are arbitrarily close at the time of emission, but are going to be arbitrarily large at the time of observation. Yeah? So anything that's very, very far right now would actually be very close at the time of emission, and you can observe them. But after some point, so these were maybe just quarks at the time, and then when they form stars and so on and so forth, their proper distance by the time they start emitting light is perhaps over this limit, and then you won't see those objects as stars. But this doesn't mean that those objects are not connected to you at all. It's just that their very early form is connected, not their later form. Okay, so that's all I want to say about this section, I think.